Welcome back. In this video we will continue our discussion on the design rules of the crystalline silicon solar cell. We will discuss metal contact grid and the design rules for reduction of optical losses. The electrons are collected at the contacts. Let's look how the contact grid looks like. The classic metal grid pattern on top of a solar cell looks like this. It's the road map for the electrons. Indicated in red, we see the highway for the electrons in the middle of the top surface of the solar cell. These are called bus bars. The smaller country roads going from the bus bar to the edge of the solar cells are called fingers. First, the fingers have a resistance R. If L is the length of the finger and W is the width of the finger and H is the height of the finger, and rho is the electroresistivity of the metal, we can describe the resistance R as rho times the length divided by the height and the width. The equation shows that the longer the path length for an electron will be, the larger the resistance the electron experiences. In addition, the smaller the cross-section, width times height of the finger, the larger the resistance will be. Note that the resistance of the contacts will act as a series resistance in the equivalent electric circuit. Large series resistances will result in low fill factors of the solar cell as discussed in part 1 of the solar energy MOOC. This means that you would like to have the finger cross-section as large as possible. In this figure, we see that the electrons in the emitter have to travel in the lateral direction to arrive at the contact. Since the N-type silicon has a higher resistivity as the metal, the charge carriers in the emitter layer also experience a resistance. In one of the exercises in this week, it is demonstrated that the power loss due to resistivity of the emitter layer scales with the finger spacing to the power 3. On the other hand, the metal contact grid is also responsible for optical losses. As the metal contacts are at the front surface, they act as an unwelcome shading object. Or in other words, light incident on the front area cannot be absorbed in the PV active layers. So you would like to keep the contact area as small as possible, which is in competition with the fact that you would like to have a largest possible cross-section. So basically, you would like to have a small as possible width and a high as possible height to comply with these requirements as demonstrated by the left contact. As you see, we have several effects which are in competition. Let's look for a moment at the relation between losses and the finger spacing. With increasing finger spacing, the power losses of the solar cell decreases due to shading. In contrast, the losses due to resistivity in the metal layer and the metal fingers increases. This means that the total loss has a minimum. Similar plots can be made for the width of the contact. The larger the width, the larger the losses due to shading. The resistive losses in the metal fingers decrease with increasing finger width. Again, there exists a width which has a minimum loss. Optimizing the front contact pattern is therefore a complex interplay between the finger width and spacing. Up to now we have talked about managing the charge carriers. Now we are going to discuss the management of the photons in the crystalline silicon solar cell device. The optical loss mechanisms are shading, reflection losses, parasitic absorption losses in the non-PV active layers, and light that is not absorbed in the silicon layers and is lost at the back contact. Shading losses are caused by the front contact grid as discussed earlier. The optimum contact grid at the front is a competition between reduction of the shading losses and a reduction of the resistivity losses in the metal contact and the emitter layer. Secondly, the reflection at the front surface can be considered as a loss mechanism. In part 1 of the solar energy MOOC, we already have discussed two approaches to reduce these losses. The first one was based on the Rayleigh film principle. By putting a film with a refractive index smaller than that of the silicon wafer between air and the wafer, you can reduce the losses. The optimum value for the refractive index of the intermediate layer equals the square root of the product of the refractive indices of the two other media. For silicon and air at 500 nanometers, this leads to an optimum refractive index of around 2.1. Note that in practice a solar cell is encapsulated under a glass plate. The glass plate will be beneficial to refractive index grading as well, reducing the total reflection losses further. Secondly, using the concept of destructive interference, we can choose the thickness and refractive index of an anti-reflection coating such that in a certain wavelength range the irradiance coupled out of the solar cell is minimized. The light reflected from the front surface is in antiphase with the light reflected from the back surface as discussed in part 1 of the solar energy MOOC. The thickness of such layer should be the wavelength divided by 4 times the refractive index. If we take a welcome reflective index of 2.1, we arrive for light of 500 nanometers at an optical thickness of 60 nanometers for an anti-reflection based on destructive interference. As we have discussed earlier, one of the typical passivation layers of standard crystalline silicon is silicon nitride. Here we see a multicrystalline silicon wafer without the silicon nitride layer. We see that a lot of light is reflected by the wafer. Next to it, we see a multicrystalline silicon with a silicon nitride passivation. As you can see, much light is reflected. Interestingly, the refractive index of silicon nitride is in the range of 2 up to 2.2 at 500 nanometers, close to the optimum for the refractive index grading approach. Typical thicknesses are in the same range as the 60 nanometers discussed earlier. Note that the surface of the solar cell looks a bit bluish. This shows that the reflection of blue light by the silicon nitride is larger than for other wavelengths. As discussed in the first part of this MOOC, texturing of the surface can improve the light incoupling as well. Light that is reflected at the textured surface can be reflected at angles in which the trajectory of the light ray is incident somewhere else on the surface. Here, the light can be still coupled into silicon. Secondly, the scattering at the textured surfaces will couple the light under angles into the wafer. This means that the absorption path length will be enhanced. This certainly enhances the welcome absorption of the light with a wavelength above 900 nanometers. The texture on the wafers can be realized with a wet etching approach. Here you can use an interesting property of the 100 surface. This anisotropic etching can be used when etching a crystalline silicon wafer with initial 100 surface orientation as shown on the left. Etching of such wafer leads to textured surfaces with pyramid structures having only the 111 orientation, as shown in the middle. In this picture you can see such textured surface of a monocrystalline silicon wafer as processed at the Else Kooi lab in Delft. Using such etching procedures, it's even possible to have a silicon wafer looking black as shown in the picture on the right. Here we see a flat multicrystalline silicon layer with and without the silicon nitride. Under these wafers we see 2 wafers with and without silicon nitride layers as well. The only difference is that the 2 wafers at the bottom have textured surfaces. The wafers are placed in the same illumination conditions as the flat wafers. By eye, you can already see that these surfaces are darker and therefore reflect less light. Now that we have minimized reflection of light at the front surface, we will shortly talk about the parasitic absorption losses. These losses refer to light that is absorbed in layers that do not contribute to the generation of electron hole pairs and thus where no photovoltaic power is generated. One of the layers of the top of the PV active layers is the silicon nitride passivation layer. The absorption curve of the material is shown here. We can clearly see that at short wavelengths, some of the incident light is absorbed such that the external quantum efficiency of the solar cell is reduced in this wavelength range. We will now turn our focus towards the back of the solar cell, where light can be transmitted or absorbed at the back surface. When light has not been absorbed in the silicon wafer after passing through the bulk, part of the light might escape at the back surface. The most obvious solutions to this problem would be to increase the thickness of the absorber layer. In fact, 1 mm of silicon will absorb virtually all photons up to the band gap of silicon. However, the maximum thickness of the wafer is limited by the diffusion length of the electrons in the p-type silicon, as these electrons need to travel from the point of generation all the way to the front surface. It would not make sense to generate electron hole pair close to the back surface when the electrons will likely not even reach the p-n junction at the front. Of course, material costs are higher if more material is used. But if we neglect the cost issue for now, another strong argument to limit the thickness of the wafer exists. The thinner the wafer, the smaller the Shockley-Reed-Hall recombination in the bulk, the higher the open circuit voltage will be. Now, since the path length of light through the material is the issue, there are two other useful solutions. One method is to use a back reflector, which is in a standard crystalline silicon solar cell design, present in the form of a fully metallized back contact. Other methods are using a material with a different refractive index such that the light is internally reflected. The reflection at a metal back contact is roughly 90% for aluminium, such that it is equivalent to almost doubling the path length of the light reaching the back of the solar cell. Combined with surface texture, we can increase the path length even further, since light will be scattered and coupled into the device at an angle. Texturing the wafers is therefore also a useful tool to limit the thickness of the wafer while maintaining the short circuit current densities and increasing the open circuit voltage. Summarized, we have discussed the general design rules for crystalline silicon solar cells on how to reduce the Shockley-Reed-Hall recombination losses and the optical losses. In the next block, I will show you various different concepts of high efficiency crystalline silicon solar cells. As you will see, they are based on the design rules we have discussed in this video. So, see you in the next video.